In this video, we will learn about the eigenvalue, eigenvector, characteristic equation, and polynomial with an example. The question is, consider the matrix. We have a square matrix A is equal to 3 minus 2, 5 minus 4. We are supposed to find out the eigenvalue, eigenvector, characteristic polynomial, and the characteristic equation. Okay? Now, to solve this, first we should understand what is meant by all the terms here. We are being told, and the definition is simple: if we have a matrix A of order n times n, that means we have a square matrix. We say this scalar lambda is called the eigenvalue of this vector, this matrix A, if there exists a non-zero vector x such that this relationship holds. Okay, simple thing. If we have a square matrix A, I am saying this scalar lambda is the eigenvalue of this matrix if there exists a vector x, non-zero vector x, such that A, that means the square matrix times this non-zero vector, is equal to this scalar times the non-zero vector x. If the relationship holds, we say this lambda is the eigenvalue of A. With this example, you will get it all. Okay, so simple thing, we are saying that this scalar is eigenvalue of this matrix A if there exists a vector x such that A times x is equal to lambda times x. Okay, so this x is called the eigenvector corresponding to the value of lambda. Okay, when we equate this, that means ax transposing this lambda x here, it will become minus lambda x is equal to 0. Okay, then what we do, we factor out x, that is the vector common, so we will be left with A minus lambda times the identity matrix. Okay, when we factor out, identity matrix remains here, and when we set it equal to 0. Now when we expand the determinant of A minus lambda I, we get the characteristic polynomial. And when we set this characteristic polynomial equal to 0, we get the characteristic equation. Okay, so let me explain it with this example. So what we have here, let us see. We have a matrix A, so let's first try to write this equation, characteristic polynomial. Okay, first we will find characteristic polynomial. For that, what we need to do, we want to construct a matrix that is A minus scalar times I. Okay, we are coming to the this example now. Now what is A? A is 3 minus 2, 3 minus 2, 5 minus 4. Okay, to this we subtract the scalar times the identity matrix, that is 1 0 0 1. Okay, that implies when we solve this, what will happen, it will become 3. Okay, 3 minus 2, 5 minus 4 minus lambda is multiplied to each of the elements here, so it becomes lambda into 1 is lambda, lambda times 0 is 0, lambda times 0 is 0, and lambda times 1 is lambda. Solving it again, it implies now 3 minus lambda, the first term will become 3 minus lambda. Here minus 2 minus 0 is minus 2. Here we have 5 minus 0. We are subtracting the corresponding elements in two matrices. Okay, so we have 5 minus 0 is 5. Then we have minus 4 minus lambda, minus 4 minus lambda, which implies that our A minus lambda I is equal to this matrix, that is 3 minus lambda minus 2, 5 minus 4 minus lambda. Okay, now to find out the characteristic polynomial, what we need to do, we need to find the determinant of this. Okay, so we can find the determinant like this, that is a minus lambda I. This denotes the determinant symbol. How do we find out the determinant? Simply we multiply the elements in the principal diagonal. That means this element and this element. That means we multiply 3 minus lambda with minus 4 minus lambda minus 4 minus lambda. Then we subtract and multiply these two elements, that is minus 2 and 5. That is minus 2 and 5. So we will get, when we solve this, I don't have the space, let me solve it here first. So we have here 3. Let's multiply 3 with these terms first. So we will get 3 times minus 4 minus lambda. Then we have minus lambda, again minus 4 minus lambda. Then we have minus into minus is plus, 2 5s are 10. Solving this, it will become 3 4s are minus 12 minus 3 lambda, minus into minus is plus 4 lambda, plus lambda square, plus 10. Let's write it in standard form. That is, we write the lambda square first, then plus 4 lambda minus 3 lambda is plus lambda, minus 12 plus 10 is minus 12 plus is minus 2. Okay, when we solve this, we will get a minus lambda I is equal to lambda square plus lambda minus 2. Okay, this is what we call this characteristic lambda I. We call this characteristic polynomial. Okay, now when we set this characteristic polynomial equal to 0, we get the characteristic equation. That means when we set a minus lambda I equal to 0, which implies lambda square plus lambda minus 2, we get, this is called the characteristic equation. Okay, ACTERIST, characteristic equation. Okay, now when we solve this characteristic equation, we will get the eigenvalues. Okay, so this is a quadratic equation. We can factor out it like this, that is, we have lambda square separating middle term. So sum of the two numbers should be equal to the coefficient of the middle term, which is 1, and the product of the same two numbers should be equal to the constant term, which is minus 2. Simple thing, we can write it here 2 minus 1. So 2 minus 1 is 1, and 2 into minus 1 is minus 2. Okay, so we can write it here plus 2 lambda minus lambda, then we have minus 2, and when we set it equal to 0, solving again, let us factor out lambda in the first two terms. We will be left with lambda plus 2, and let's take minus 1 common from the last two terms. We will be left with lambda plus 2, and we set it equal to 0. Solving it further, that means lambda minus 1 is equal to 0, lambda minus 1 is equal to 0, which implies lambda is equal to 1, or lambda plus 2 is equal to 0 implies lambda is equal to minus 2. So we got two eigenvalues, that is lambda is equal to 1 and lambda is equal to minus 2. These are called the eigenvalues. Okay, I hope I am making myself clear. So when we set characteristic equation equal to 0, we get the eigenvalues. So characteristic polynomial we got, eigenvalue we got. Now we need to find out the eigenvector. Okay, to find out the eigenvector, what will we do? Basically, there will be, the corresponding what we call the eigenvectors are found by using those values of lambda which we got here in the equation. In this equation, a minus lambda times sorry, lambda times identity matrix times x. When we set it equal to 0, we will get the eigenvector. Okay, so to find out the eigenvector, what will we do? We simply plug lambda is equal to, first lambda is equal to 1, okay, in what equation? um, in this equation, okay, in this equation, let us say this is equation 1, in equation first. Simple thing, to find out the eigenvector, what we do, we simply plug first this eigenvalue 1 is equal to, sorry, lambda is equal to 1 into this equation, a minus lambda I into x is equal to 0 in this equation. So what will we get? So in place of, we have the equation a minus lambda is 1, so we will write I times x is equal to 0. Okay, solving this, we will get the corresponding eigenvector. So a, what is a? I have the space here. Okay, so we know that a is this matrix 3 minus 2, 3 minus 2, 5 minus 4. Then we have minus this I is 1 0 0 1 identity matrix, and this is being multiplied by the eigenvector x. So x, we can write it as x1 and x2, and when we set it equal to 0, when we solve for x1 and x2, we will get the eigenvector. Okay, let me see if I have the space to solve this stuff. So let's do the shortcut here. So we will get here 3 minus 1 is 2. Okay, so let me write it here. 3 minus 1 is 2. Minus 2 minus 0 is minus 2. 5 minus 0 is 5. Minus 4 minus 1 is minus 5. And we multiply it with this eigenvector x1 and x2. Okay, to find out the values of x1 and x2, and we set it equal to 0. Now we need to solve this. So we multiply here using the matrix multiplication, that is, we multiply each row with corresponding column. So when we solve this, so we will get 2 into x, 2 into x1 plus 5 into x2, 5 into x2. Simple, we are doing the matrix multiplication, and I have to be very careful here, not to go out of the boundary. Okay, I have the limited space here, so I am multiplying this row with this column and writing it as the first element, that is mean in the row form. Then I multiply this row with this column, so we have minus 2 x1, then we have minus 5 x2. So we got this very matrix, and we set it equal to 0. Okay, it is very simple. We are doing the matrix multiplication. Okay, so we multiply this row with this column and we write it here. Okay, then we multiply this row and this column and write it here, so we get a column matrix here. Solving these two equations implies either 2x1 plus 5x2 is equal to 0, and minus 2x1 minus 5x2 is equal to 0. Okay, now if we solve these two equations, and where do we write it here? I don't have the space for that. I have to rub something. Okay, let me rub this out. When we solve this, we will get 2x1 is equal to minus 5x2, which implies x1 will be equal to minus 5 upon 2 x2. Okay, so the value of x1 came out to be this, and I can rewrite it as x1 is equal to minus 5 upon 2 times a scalar. Okay, this is the value of this x1. Now we plug x1 is equal to this stuff in this equation to get the value of x2. So in place of x1 we have minus 5 upon 2 times this scalar is equal to minus 5 upon 2 times x2. That means minus 5 upon 2 minus 5 upon 2 gets cancelled, which implies x2 will be equal to this scalar. Then what will be what we call our characters, sorry, the eigenvector. One of the eigenvector will be, and let me write it here, our eigenvector will be equal to scalar, and let us rewrite it here. So we got x1 is equal to minus 5 upon 2 s, and x2 is equal to s. Let us take s common. That means our s is common. We are left with minus 5 upon 2 and 1. This is one of the eigenvector. Similarly, when we put lambda is equal to minus 2 in this equation, we will get another what we call the eigenvector corresponding to this lambda is equal to minus 2. Okay, when lambda is equal to 1, we got this eigenvector, which is equal to scalar times this, the value of x1 and x2. I hope I make myself clear in this video. Thank you.